Okay, today I want to talk about molecular geometries. Um, to do this, we're going to have to draw the Lewis dot structure of the compound first, and from that, we'll be able to determine the molecular shape. Before we get to that, we're going to have to talk about a little background stuff. So we talked about polar covalent bonds before, but let's reintroduce it because it's going to be necessary when we're drawing these molecules. So a covalent bond, of course, is a chemical bond in which a pair of electrons are being shared between two nonmetal atoms, or a nonmetal and a metalloid. And for a nonpolar covalent bond, those pair of electrons are basically being shared evenly between the two nuclei. Now, of course, we know that these electrons are moving all over the place, but on average, we know that they're going to be approximately between the two positively charged nuclei, and then this pair of negatively charged electrons is what is holding together these two atoms through the attraction of the positive and negative charges. Now, on the other end of the spectrum, we have ionic bonds. Okay, so in an ionic bond, there's no sharing of electrons. In this case, the lithium gave up its a single valence electron to the fluorine, which now allows fluorine to actually have 8 valence electrons. In the process of giving up that one electron, well, that leaves the lithium with a +1 charge. And because the fluorine picked up an extra electron, it's left with a -1 charge. And so an ionic bond is, again, just the attraction between this fully positive charged ion here and this fully negatively charged ion over here. And again, a very strong bond. So these are both chemical bonds. They're both very strong bonds. But a lot of covalent bonds actually are in this fuzzy center in between. And we're going to find out that the sharing of the electrons actually depends on what's called the electronegativity of the atom. And that basically is the ability of an atom to draw the bonding pair of electrons closer to themselves. And this is going to be due to a difference in electronegativity. So we're going to see that each atom has its own electronegativity. So for example, if we look at the molecule hydrogen fluoride, what we're going to find out is that the fluorine has a very high electronegativity. In fact, it has the highest electronegativity of all the elements. And hydrogen actually has a very low electronegativity. So basically what that means is that the fluorine is going to pull on this pair of electrons more than that of the hydrogen. And so that pair of electrons, instead of sitting in between the two nuclei, is actually going to be closer to the fluorine. Now, it's not fully taken over like the ionic fluoride over here, but it is spending more of its time by the fluorine rather than the hydrogen. Now, as you can imagine, this is going to cause a difference in charge. So the negative charge now is closer to the fluorine, and the nucleus is being partially exposed because the electrons are so far away from it over here. So the electronegativities are different for all of the elements. And so here's the Pauling scale. And so again, we can see fluorine has the highest electronegativity at 4.0, and cesium and francium below it have the lowest electronegativity. Now, we assume that the noble gases have a 0 electronegativity. Now, that's actually not true, but for the purposes of drawing these compounds, it works. So again, if one of these noble gases happens to be part of a compound, it's going to be the least electronegative of all the elements within that compound. And so basically, you can see that the electronegativity decreases as we go down a group. And it also decreases as we go from right to left across the period. Okay, so that's all you're really going to need to know. Okay, I don't expect you to know the actual values of the Pauling scale, but the fact that fluorine has the highest electronegativity, cesium, francium have the lowest electronegativity. So the electronegativity again drops as you go down a group, and it drops as you go from right to left across the periodic table. There is going to be one bond, the carbon-hydrogen bond, that I do expect you to know the polarity of. And as we're going to see, it's basically a non-polar bond. But otherwise, everything else you can get from the trend on the periodic table. Now, because these electrons are shifted towards the fluorine, like I said, this side of the bond, in this case, the molecule, is going to be slightly negative because those electrons are hanging out more on this side, right? So we represent that partial negative charge. It's not like the full -1 negative charge that we just seen for the fluoride ion. But in this case, we use the delta minus, which simply means that it's not a full minus. It's a partial negative charge that's on the fluorine. And again, we're exposing the nucleus a little bit by having these electrons farther over here. And so this side of the bond is actually slightly positive. Now, the difference in electronegativity of these two elements, 2.1 for the hydrogen, 4.0 for the fluorine, gives us a difference of 1.9. Now, there is no set value to say where we go from a molecular compound to an ionic compound. Generally, it's around this value here, 1.8, 1.9. But the way we're always going to look at it is that two nonmetals, or a nonmetal and a metalloid element, are going to form covalent bonds, and a metal and a nonmetal are going to form ionic bonds. So we're never really going to use these numbers, these exact differences. Again, it's kind of a fuzzy area. Now, the only bond that I do want you to know is that of the carbon-hydrogen bond. It has a very small difference in its electronegativities, and therefore it's pretty much evenly sharing that bonding pair of electrons between the carbon and hydrogen. And so we basically say that the carbon-hydrogen bond is essentially non-polar. So again, this is the only one that I actually want you to know. The other ones we can get from the trend on the periodic table. So we're going to refer to these dipoles, we're going to call them dipole moments. So basically, we are going to use a vector. And a vector is basically a value that has a scalar portion. So in other words, it has a certain value to it, a magnitude. And it also has direction to it as well. And so we're going to always show this dipole as an arrow with the plus side on the less electronegative atom and the arrowhead side on the more electronegative atom in that particular bond. And so this is going to be our vector that we're using. We're going to call this a dipole moment. Similar to a structural formula, the Lewis electron dock formula of a molecule shows how the atoms in a molecule are bonded. And whether they're single, double, or triple bonds. In addition, it's going to show us the position of all the lone pairs. Now, this is not telling us how the atoms actually sit in three-dimensional space. This is just telling us what's connected to what and where the lone pairs are. So, for example, here we have the chlorine molecule. And basically, we have a bonding pair of electrons. So these are going to be the electrons that are shared. And again, we could have 2, 4, or 6, depending on whether it's a single, double, or triple bond. And then we have these outer electrons that aren't bound to any other atom, and we call these things lone pairs, and they generally are in pairs. There's few exceptions where we'll only have a single electron rather than two, but in almost all instances, they're going to be paired up. So we're going to have these lone pairs of electrons that, again, aren't bound to any other atom. Now, generally, we don't show the dots for the bonding electrons. We draw a single line for each set of bonding electrons. So for a single bond, we're going to put a single line between the two. If it was a double bond, we'd draw 2 lines between the two. And if it was a triple bond, we'd draw 3 lines between the two. And this is basically how we're going to write our Lewis dot structures. Okay, so a few rules for actually writing Lewis dot structures. First, you got to determine the total number of valence electrons that you're going to need to draw that molecule or polyatomic ion. And if it is a polyatomic ion, you're also going to have to account for the charge. So basically, we're going to add up all of the valence electrons for each individual atom, we're going to assume they're all neutral. And so we're going to add up all the valence electrons. And then if it is an anion, well, that means it has extra electrons. So we're going to add whatever that charge is. If it's a -1, we're going to add 1 electron. If it's a -3, we're going to add 3 electrons on top of all the other valence electrons. And if it's a cation, well, that means it lost electrons. So we're going to subtract that same number of electrons as the charge. Next, we're going to have to draw the skeleton structure. This is basically just showing what atoms are bound to what. And the central atom has other atoms bound to it. You could actually have more than one central atom, as we're going to see later on. But the central atom is generally the least electronegative atom. Now, of course, there's going to be exceptions to that. Hydrogen, for example, can never be a central atom. Then we're going to connect each atom to one another with a single bond to start with. So we're going to use two dots, or we're actually going to use dashes. And you're going to have to deduct 2 electrons from the total number of electrons for each bond that you form. Next, we're going to start with the outer atoms, the more electronegative atoms, and we're going to start fulfilling the octet for each one of those atoms. So we're going to make sure that each is surrounded by 8 electrons. Those include the bonding atoms as well. And of course, for hydrogen, the octet is only 2, but for all other atoms, that's going to be 8. If we're short electrons, we're going to form multiple bonds so that we, again, try to get to that octet. And if we have extra electrons, well, they're going to go on the larger atom that can generally handle it. As it turns out, the larger atom is generally the least electronegative atom, so it's always our central atom. And so that's where we're going to put them. And then we'll talk about this rule where we can't violate the octet rule for period 2 elements. We'll talk about that later on. Okay, so let's do a few examples. So let's draw the Lewis dot structure for phosphorus trichloride. So first thing we need to do is determine the number of valence electrons for each. Okay, so if we look at the electron configurations for phosphorus and chlorine, we can see that the outermost electrons are valence electrons. So there's the 2s and the 3p. So that's a total of 5 valence electrons. And for the chlorine, again, it has a 2s and 5p. So it's going to have a total of 7 electrons. But we don't need to draw the electron configurations every time. For the main group elements, of course, you'll notice that, again, we said phosphorus has 5. Well, phosphorus is in group 5 and therefore has 5 valence electrons. And we said chlorine has 7. Well, chlorine's in group 7 and thus has 7 valence electrons. So we're not going to need to draw the electron configurations every time. We can simply use the A values on the periodic table for the main group elements. Now, of course, that doesn't work for the transition metals, but it certainly does work for all of the main group elements. Okay, so phosphorus, as we said, has 5. Chlorine, the chlorine has 7. Now there's 3 chlorine, so we're going to have to multiply that by 3, and then we're going to add it up. What 21 plus 5 is 26, so we have 26 electrons that we need to place. Our next step is going to be to draw the skeleton structure. So again, we're going to assume for the most part that we have very simple molecules. We have one central atom, and then all the other atoms are going to be connected to it. Now, again, there are going to be exceptions to that. And with doing your homework and watching these lectures, of course, you're going to be able to pick up on those exceptions. Okay, so first thing we need is the less electronegative atom. It doesn't matter how many there are. We need the least electronegative atom. Fluorine, of course, is the highest electronegativity. Francium, the smallest electronegativity. And I can see that chlorine is closer to fluorine than the phosphorus. Therefore, phosphorus is less electronegative than the chlorine. So phosphorus is going to be our central atom. Next, we're just going to connect all the chlorine with single bonds. So there's 1, 2, 3. Okay, so now in the process, we used a total of 2, 4, 6 electrons. So we still have 20 to place. Now, like I said, we're not going to use dots. Okay, we're not going to use dots like this. We're going to use lines. So just remember that each line represents 2 dots. So we use 2, 4, 6 electrons. We have 20 left. Our next step now is going to fulfill the octet for the outer, more electronegative elements. So right now, let's look at this chlorine. So it has 2 electrons so far. So now let's go with 4, 6, and 8. This one also has 2, 4, 6, 8. This one has 2, 4, 6, 8. So now we've used 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. We still have 2 left. Okay, well, that's good because the phosphorus still only has 2, 4, 6. So we'll put that pair of electrons there. And now we have fulfilled the octet for all the atoms in this molecule. Now, as we're going to see, this is only the first step. So the octet roll in these set of rolls gets us to the most probable structure quickly, but it's going to be the formal charges that are actually going to determine whether this is the most probable structure that we're going to find in nature. So again, drawing this and following the octet rules, the first step. The second step is going to be to look at the formal charges, and we'll look at that in just a minute. Okay, so we used up all of our electrons and we're good to go. Okay, let's try it again. This time, let's draw the electron dot formula for acetic acid. Now, remember we talked about structural formulas, right? So, and we talked about the different organic functional groups. Well, this you should recognize right here. Okay, that is a carboxylic acid. Okay, so this gives us a clue of how to actually draw this structure. So again, we got to determine the number of valence electrons. So again, we have the carbon. Well, we look at the periodic table, we can see that carbon's in group 4, so it has 4 valence electrons. There's 2 of them, though, so we're going to have to multiply that by 2. Then I see hydrogen, okay, and hydrogen's in group 1, so it has 1 valence electron. And I can see there's 4 hydrogens, so we'll have to multiply that by 4. Then we have oxygen, so we're going to have to add the valence electrons of oxygen to that. I see there's 2 of them. So oxygen is in group 6, so it'll have 6 valence electrons, but there's 2 of them, so we have to multiply that by 2. Add all that together, and we have a total of 24 electrons that we need to take care of. Now, again, we're going to draw the skeleton structure next, but a couple of clues. First, this is a structural formula, so it's basically telling us what is bonded to what. And on top of that, we're going to recognize that this is a carboxylic acid. So first, let's start with this, right? So we know that we have the carbon, and as we discussed in class for organic molecules, it's really easy. If it has 4 valence electrons, it's going to make 4 bonds. So we know that 3 of them are going to be with these hydrogens. So there's the carbon, and then there's the 3 hydrogen. Now, again, we know that this carbon then must be bound to this carbon here. So that carbon is going to be next, and that, of course, is part of this carboxylic acid group. So that carbon is going to be next. And we know in a carboxylic acid that this carbon is bound to both of these oxygens. So both of the oxygens, and this hydrogen is bound to one of the oxygens. So we'll just put it there. Okay, so there's our skeleton structure. We've used up 2, 4, 6, 8, 10, 12, 14 electrons. So we still have 10 electrons left. Our next step, of course, is going to be to fulfill the octet of the outer more electronegative atoms first. So let's start with this oxygen. It has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. And let's see, we used up 2, 4, 6, 8, 10. Oh, we used up all the electrons, but we have a problem here, right? This carbon fulfilled its octet. Hydrogen, of course, only ever gets a single bond. It has an octet of 2, so that one's good. But this carbon has 2, 4, 6. The oxygen are both good, but we're short electrons. Now, remember, if we're short electrons, we're going to form multiple bonds. Now, one thing to know is that multiple bonds most likely are going to involve carbon, nitrogen, oxygen, and sulfur. So it's probably going to be somewhere in here. Now, we're going to find out through formal charges that the formal charges will actually let us know exactly which lone pair that we need to take to make a multiple bond. Okay, so we'll do that a little bit here in a little while. But for now, we know that a carboxylic acid anyway, we know that this is a double bonded oxygen. So we're going to take this pair of lone pair, and we're going to make it a bonding pair of electrons at this point right here. Okay, so there it is. We've used up all of the electrons, and we have the most probable structure. We don't know that yet, of course, until we would determine the formal charges, but we have fulfilled the octet for all the atoms in this molecule. Okay, now let's talk about formal charges. So formal charges are assigned to atoms within a molecule, and they're used to predict the most probable structure of a molecule or ion. So half of the electrons in a bond are going to be assigned to each atom associated with that bond. Lone pairs of electrons, the unshared pairs of electrons, are going to be assigned to the atom in which they belong. And basically, we could use this little formula here, this little equation. Later, I'm going to show you a much easier way, but this is the formal equation for formal charge. So basically, we're going to take the valence electrons of a given atom. Again, we're going to assume it's neutral, so whatever the group number of that atom is. We're going to subtract 1/2 of the bonding electrons, right? Because half go to one, half go to the other. And then we're going to subtract the lone pair of electrons from it, and that's going to give us the formal charge. So the sum of the formal charges are going to be equal to 0 for a neutral molecule, or they're going to equal the charge of the polyatomic ion. So let's go through some rules for actually using formal charges. So the best Lewis structure is going to be one in which all of the charges are 0. Now, this is going to be for a neutral compound. If we have a polyatomic ion, we want all the charges, formal charges of all the atoms, except for one to be 0. And then that one will have the charge of whatever that polyatomic ion is. Now, we're going to see that we can't always put the whole charge on a single atom. Most of the time, we have to actually distribute that over a few of the atoms. If a Lewis structure has non-zero formal charges, then the one with the fewest non-zero formal charges is going to be the preferred by nature. A Lewis structure with an adjacent formal charges should have opposite signs. So if you have two atoms that are bound to one another and they both have formal charges, one better have a positive formal charge and the other a negative formal charge. And then when there is one Lewis structure possible that has to have a non-zero formal charge, we want the negative formal charge to go on the more electronegative atom. And like I said, there's times that we have to violate these different rules. Okay, so example, what's the most probable structure of carbon dioxide? So we have these three possible structures, right? I have fulfilled the octet for all of these guys. And so we'll come back to why some of them shouldn't have even been written to begin with, but here it is, right? So let's try this. So again, there's our formula for formal charges. So first thing we need to know is the number of valence electrons. So again, looking at the periodic table, I can see that oxygen is in group 6. So all the oxygens have 6 valence electrons, and the carbon is in group 4. So it has 4 valence electrons. Okay, now let's do the formal charges. So let's start with this oxygen right here, right? So this oxygen has 6 valence electrons. We want to subtract half of the bonding electrons. Well, there's 2, 4, 6. Remember, each line represents 2 electrons, so there's 6. And then the lone pairs, there's 2 lone pair electrons. So 6 minus 3 minus 2 is positive 1. So this oxygen has a formal charge of positive 1. Next, let's look at the carbon. So carbon's in group 4, so 4 valence electrons. It has a total of 2, 4, 6, 8 bonding electrons, and there's no lone pair. So 4 minus half of 8, which is 4, minus 0 is 0. So this carbon has a formal charge of 0. Next, let's look at this oxygen here. Again, in group 6, and there's 2 bonding electrons, and then there's 2, 4, 6 lone pair. So 6 minus 1 minus 6 is negative 1. So this oxygen has a negative 1 formal charge. Okay, going down the line, next oxygen. Again, in group 6, so 6 valence electrons. There's 2, 4 bonding electrons, and there's 2, 4 lone pairs. So 6 minus 2 minus 4 is 0. So this oxygen has a 0 formal charge. Let's come to this carbon, right? And this oxygen, by the way, is identical, right? It has a double bond, it has 2 sets of lone pairs, so its formal charge must also be 0. So let's look at this carbon now. Again, group 4, so 4 valence electrons. It has a total of 2, 4, 6, 8 bonding electrons, and there's no lone pair. So 4 minus 4 minus 0 is 0. So this has a formal charge of 0. Okay, moving on. Let's go to the next one. So this oxygen, of course, is an oxygen with a double bond, 2 sets of lone pairs. So we've already calculated its formal charge at 0. This one we haven't. So this oxygen's in group 6. It has a total of 2, 4, 6, 8 bonding electrons, and there's no lone pairs on it, so 0. So 6 minus 4 is equal to plus 2. So that has a plus 2 formal charge. And then we have this carbon here. So this carbon is in group 4, so it has 4 valence electrons. It has 2 4 bonding electrons and 1, 2, 3, 4 lone pairs. So 4 minus 2 minus 4 is negative 2. So that has a negative 2 formal charge. Okay, so now we got to sit here and think of which one of these is the most probable structure. Well, we could eliminate this guy right off the bat, right? We didn't actually follow the initial rules. The least electronegative atom should be the central atom. And we know that oxygen is closer to fluorine than carbon. And so carbon is the least electronegative atom. So this structure we should have never chosen because we didn't follow the rules to begin with, okay? And the formal charges bear that out. We'll come back to that here in a second. Then we come over to here. Well, we fulfilled the octet for everything, but we have 2 non-zero charges, okay? We have 2 non-zero charges, and this structure has all 0 charges. So this is going to be our most probable structure. Now, let's look at the other ones. So a few other things here, right? So another problem with this structure is that our negative formal charge is actually on the least electronegative element, so that's not a good thing. Over here, though, our negative charge was on the more electronegative element, so that's actually a plus for it. One plus for this is that it does have adjacent atoms, and they do have opposite a sign of their formal charge. But again, this is going to be the most probable structure because it has all 0 formal charges. Okay, let's try I'm sorry, let me come back to this too. I want to show you an easier way to calculate the formal charges. So the easiest way to do it is just to take the number of valence electrons. So this is oxygen and it has 6. And we're going to subtract 1 for each line and 1 for each dot. So 6 minus 1, 2, 3, 4, 5. 6 minus 5 is positive 1. So 4 valence electrons for carbon. So 4 minus 1, 2, 3, 4. 4 minus 4 is 0. We have oxygen in group 6. So 6 valence electrons minus 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is negative 1. So it's a lot easier way and quicker way to calculate the formal charges rather than using this equation. Okay, let's try another one. This time, let's try for N2O or nitrous oxide or dinitrogen monoxide. And let's say we have 3 possible structures that we draw. And let's go through the whole process again. So again, we got to know the number of valence electrons. Well, nitrogen's in group 5, oxygen's in group 6. And so there's the valence electrons. Now let's start calculating the formal charges. Well, if nitrogen's in group 5, 5 minus 1, 2, 3, 4, 5. 5 minus 5 is 0. Nitrogen's in group 5, minus 1, minus 2. No. 5 minus 1, 2, 3, 4, 5. 5 minus 5 is 0. Oxygen in group 6, minus 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. Let's go to this nitrogen. Nitrogen's in group 5, minus 1, 2, 3, 4, 5, 6. That's negative 1. 5 minus 6 is negative 1. Group 5, minus 1, 2, 3, 4. 5 minus 4 is positive 1. Oxygen in 6, minus 1, 2, 3, 4, 5, 6. That's going to be 0. Nitrogen again in group 5, minus 1, 2, 3, 4, 5, 6. So negative 1 again. Oxygen in group 6, minus 1, 2, 3, 4. 6 minus 4 is positive 2. Nitrogen in group 5, minus 1, 2, 3, 4, 5, 6. 5 minus 6 is negative 1. Okay, so now one thing I should also mention is that the sum of the formal charges should equal 0 for neutral molecules, and the sum of the formal charges for ions should equal their charge. So that just tells us that we use the correct number of electrons when making a Lewis dot structure. It doesn't tell us anything about whether or not we have the most probable Lewis dot structure. They should always add up to the correct number. In this case, they're all zeros. So we use the correct number of electrons in each and every one of these structures. Okay, so next, let's look at each one of these structures. So if I look at this structure, you're probably going to guess, well, okay, well, there it is. There's the most probable structure. But I'll tell you that it isn't. Can you figure out why it isn't? Well, if you look at the nitrogen, okay, nitrogen has a total of 2, 4, 6, 8, 10 electrons around it. We're not going to be able to violate the octet rule for nitrogen. As we're going to see later on, nitrogen is a period 2 element. It doesn't have the available orbitals to violate that octet rule. Some atoms do, and some atoms do violate the octet rule by having more than 8 electrons, but nitrogen cannot. So this guy violated the octet rule. So this is impossible. Okay, so this cannot happen. It violated the octet rule. So that leaves us with these two. Well, this one has fewer non-zero formal charges than this guy. So this guy is probably the most probable structure. But the other issue here too is that oxygen is more electronegative than nitrogen, yet oxygen has the positive formal charge when it should have the negative formal charge. In addition to that, we didn't follow the rules again, right? Nitrogen is less electronegative than oxygen. So nitrogen should have been our central atom, not oxygen. So again, we didn't follow the guidelines, and the formal charges are going to play that out as well. Okay, so we're stuck with this guy here. It has 2 non-zero formal charges, but we can't do this because we can't violate the octet rule. So this is the most probable structure that we're going to find in nature. Okay, let's talk about the exceptions to the octet rule. So there's 3 types of exceptions. First, we could have molecules with an odd number of electrons, which means we're not going to have pairs. We're going to have molecules in which one atom has less than 8 valence electrons. And we're going to have molecules in which an atom has more than 8 valence electrons. So let's start with the odd number of electrons. So some molecules have no choice but to have an odd number of electrons. Examples would be carbon dioxide, nitrogen monoxide, and nitrogen dioxide. So for example, let's look at the nitrogen dioxide. So if we draw the Lewis dot structure, again, the valence electrons, well, nitrogen's in group 5, so it has 5 valence electrons. Oxygen's in group 6, so it has 6 valence electrons. There's 2 of them. So we have to multiply that by 2. And when you add them all together, we have 17 electrons. It's not an even number. Now, again, we have nitrogen and oxygen. Nitrogen is the less electronegative atom, so it's going to be our central atom. And when we draw the structure, it's going to look like this. Okay. Now, if we actually calculate the formal charges, well, oxygen's in group 6, minus 1, 2, 3, 4, 5, 6. So it actually has a formal charge of 0. Nitrogen's in group 5, minus 1, 2, 3, 4, 5. It has a formal charge of 0. Oxygen again in group 6, minus 1, 2, 3, 4, 5, 6. Again, it has a formal charge of 0. And therefore, this is the most probable structure. Now, the issue with these molecules that have odd numbers of electrons, we call these radicals because they want to react with whatever they can. Atoms want their 8 electrons, okay, or more, but they definitely want their 8 electrons. So things like chlorine dioxide, nitrogen monoxide, nitrogen dioxide, these things are all poisonous to us. And again, it's because of this highly reactive single electron by itself. Okay, next, let's talk about compounds where we have fewer than 8 electrons around each of the atoms. And these are going to occur for compounds in group 1A, 2A, and 3A. So examples would be lithium hydride, beryllium dihydride, boron trifluoride. So let's look at the lithium hydride. So First, we need the valence electrons. Lithium's in group 1, hydrogen's in group 1, so that's a total of 2 electrons. Well, if we have 2 electrons, all we can do is bind the 2 together, and nobody's going to have lone pairs. But again, it's the formal charges that's important, not the octet role. Lithium's in group 1, 1 minus 1, so it's going to be 0. Hydrogen's in group 1, 1 minus 1, so it's 0. So there it is. They have formal charges of 0, so this is the most probable structure for lithium hydride. Beryllium hydride. So again, valence electrons. Beryllium's in group 2, so it has 2 valence electrons. Hydrogen in group 1, except of course there's 2 hydrogens, so multiply that by 2, so that gives us a total of 4 electrons. That's going to allow us to make a single bond between each of the hydrogens in the beryllium. Again, let's look at the formal charges. So hydrogen's in group 1, 1 minus 1 is 0. Beryllium is in group 2. Okay, so this hydrogen's also going to be 0, but beryllium's in group 2, minus 1, 2, so that's 0. And then again, group 1 minus 1 is 0. So again, this is the most probable structure for beryllium beryllium hydride. Okay. Okay, then we come to the, so rarely we're going to deal with an odd number of electrons. Sometimes we're going to deal with less than 8. And again, it's generally going to be the boron compounds that we're going to be working with. We're not going to talk a lot about hydrides. So this is actually not ionic. It's actually covalently bound non-metal to a metal, which is kind of weird. But these are hydrides. But generally, we're going to deal with boron compounds. Those are the ones that we're going to look at, and sometimes aluminum. Okay, so now elements of the second period are limited to bonding orbitals of the 2s and the 3 2p orbitals, right? So period 2, that's n equals 2. That means the allowed L values, right, are going to be up, going to go from 0 up to n minus 1. So that's L equals 0, L equals 1. So that's the s and the p orbitals. We know that the s subshell has a single orbital and the p subshell has 3 orbitals. So that's a total of 4 orbitals. We can put 2 electrons in each orbital. Even for bonding, we can't violate the Pauli exclusion principle. So we can only put 2 electrons in each orbital. So that means there's a total of 4 bonds. So especially for carbon, nitrogen, oxygen, and fluorine, we can never violate the octet rule for any of the period 2 elements. But these are the ones that are going to be the ones that we use the most that are going to have an issue with this. So again, we cannot violate the octet rule for the period 2 elements, carbon, nitrogen, oxygen, and fluorine. There simply are no orbitals available. But once we get to the 3rd period and beyond, so for n equals 3, right, our allowed L values are going to be 0, 1, and 2. Well, that's the s, p, and d orbitals. So for these guys over here, we can make the normal 4 bonds using the s and the 3p atomic orbitals, which we're going to see later on morph into molecular orbitals. But we also have unused 3d orbitals. So we could use those unused 3d orbitals to actually form bonds or give a place for lone pairs or whatever we're going to be doing with it. So we can violate the octet rule for anything below the period 2. We cannot violate the octet rule for this period 2 elements, though. Okay, so here's some examples of violating that octet rule. So in particular, here's a xenon tetrafluoride. So xenon tetrafluoride has 34 valence electrons, and the structure is going to look like this. Notice that we put those extra pair of electrons on the central atom, because the central atom is generally the largest atom and can most easily take up those extra electrons. Plus the fluorine is in period 2, so we couldn't violate the octet rule anyway. But the point is that the extra electrons always go on that central atom. And so we have a total of 2, 4, 6, 8, 10 electrons. So we definitely violated the octet rule. Now, again, we're allowed to because sulfur's in period 3 and has those empty available d orbitals. And if we go around and calculate the formal charges, so if we look at the fluorine, right? So fluorine's in group 7. So 7 minus 1, 2, 3, 4, 5, 6, 7. Well, that has a formal charge of 0. Well, all these fluorines have a single bond and 3 sets of lone pair, so they're all going to be 0. The sulfur's in group 6, minus 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. So again, we can see the formal charges of all the atoms in this molecule are 0. So this is the most probable structure for sulfur tetrafluoride. And again, like I said, the extra electrons are always going to go in that central atom, and generally because it is the largest atom, because the size of atoms follows the same trend as electronegativity. The lower the electronegativity, the bigger the atom is going to be. Okay, let's look at something called delocalized bonding. So here is the Lewis dot structure for ozone. Now it's a weird structure, right? You might say, well, why don't you simply take this lone pair here and make it a bonding pair here? Well, I can't do that, right? Because that would put 2, 4, 6, and then the other bond would be 8 and then 10. But oxygen is a period 2 element, so I can't violate the octet rule for it. So this has to be what the Lewis dot structure looks like. Now, looking at this thing, I'm going to say, well, if I look at the structure of this thing and I measure these bonds, well, we know that multiple bonds are shorter than single bonds, right? So the single bond is the longest, then the double bond is shorter, and the triple bond is even shorter yet. So I would suspect that if I looked at the structure of this molecule, I would find that ozone has one short bond and one long bond. However, when I look at it, so again, we can see what 6 minus 1, 2, 3, 4, 5, 6. So that's 0. Here we have 6 minus 1, 2, 3, 4, 5. 6 minus 5 is plus 1. And then 6 minus 1, 2, 3, 4, 5, 6, 7 is negative 1. So that's another thing too. We're going to talk about molecular polarity. And this will be surprising if you come back and review this later. Ozone's actually a polar molecule. Now you might say, well, these are both oxygens, and so that's a non-polar bond. And these are both oxygens, so that's a non-polar bond. And that would be true, except that polarity is actually more complicated than that. It actually depends a lot on the formal charges of the molecule. And we can see that this thing is bent. And you'll notice that there's a plus here and a minus here. Well, that's a dipole. And in fact, ozone has a dipole, a moment of about 0.6 to bi. So it's a pretty polar molecule, even though it has non-polar bonds. It has to do with these formal charges. Okay, so coming back. So again, I would expect a short and a long bond, but when we experimentally look at ozone, it has 2 identical bonds. They're both 1.28 angstroms. They're both slightly shorter than a single bond, but slightly larger than a double bond. So it's kind of strange. Again, they're equal. So this Lewis dot structure isn't telling us the whole story here. So some molecules obviously are not well represented by the Lewis dot structures. Now, what really is happening here is we have what's called delocalized bonding. So some of these electrons are actually being shared between 3 atoms. And that's what this dotted line represents. Now, in higher chemistry courses, you might be using a dotted line like this. In this course, we are not going to do this. We're actually going to use normal electron dot structures to represent this delocalized bonding. And delocalized bonding occurs when a pair of electrons is being shared by 3 or more different atoms, rather than being localized between just 2 atoms. So we're going to be able to do this by using Lewis dot structures. We're going to write what we call resonance structures. And then the best resonance structures that we get are going to be part of what we call the resonance description. Okay, so this is how we're going to represent this delocalized bonding through resonance structures. So let's look at the sulfate anion. So SO4, or I'm sorry, the ozone. We're looking at the ozone, right? So the ozone has 6 valence electrons, but there's 3 of them. So we have a total of 18 electrons that we need to deal with. So we're going to draw the structure real quick. There's, oxygen has to be the central atom. We connected each. We started with the outer ones and we gave them each 8. But once we got to this oxygen, we ended up short. Now we know that we can use, lone pair electrons to make multiple bonds so that we could try to fulfill the octet for that oxygen. Right now it only has 2, 4, 6. So ideally we need one more double bond. Now we can do this by using the formal charges themselves. So if I look at this, this has 6 valence electrons, 6 minus 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is -1. Oxygen's group 6, minus 1, 2, 3, 4. 6 minus 4 is +2. And then this is identical, right? An oxygen, 3 sets of lone pair single bond. So it's -1 as well. So what you can do is that if you have 2 atoms with opposite formal charges bound to one another, you're going to take a lone pair off the one with a negative formal charge and make it a multiple bond with the one with a positive formal charge. So we're going to take this lone pair here and we're going to move it as a bonding pair right here. Well, now we have to recalculate these guys, right? Because the electrons, this one stayed the same, but these two changed because we just changed the number of electrons around them. So remember, this was -1, this was +2. Now when we recalculate 6 minus 1, 2, 3, 4, 5, 6, well, that's now 0. And this is 6 minus 1, 2, 3, 4, 5. 6 minus 5 is +1. So notice that we changed both of them by 1. And that's the way we know what atoms we should form double bonds with. But you might have said, well, wait a minute, why didn't you use the lone pair off of this one? Well, we could have done that, right? And now this has what? 6 minus 1, 2, 3, 4, 5, 6, 7. That's -1. 6 minus 1, 2, 3, 4, 5. Well, that's +1. And then 6 minus 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. And you'll notice that they both have 2 non-zero formal charges. One's a -1, one's a +1. The minus is on the oxygen. Okay. So these two structures, we could have chosen either one of them. And when you have choice of where to put electrons to get the most probable structure, you have resonance. You have delocalized bonding. And we're going to represent that delocalized bonding through what's called a resonance description. So here's our most probable structures. We're simply going to put a double-headed arrow between them. And that means that this represents the resonance description of this molecule. Now, keep in mind, for resonance structures, the atoms don't move. You always start with exactly the same skeleton structure. The atoms do not move. Only the electrons move. Okay? So there will be a different arrangement of electrons, but the atoms themselves will have the exact same arrangement. They do not move. Now, this structure doesn't flip between these two structures. It's actually the average of these two structures. Okay, so it's going to be the average. Keep that in mind as well. Okay, let's try an example. Let's draw the resonance description for the polyatomic ion, the sulfate ion. Okay, so again, first thing, of course, we need to do is going to be to determine the number of electrons that we got to use in this structure. So let's see, the sulfur, well, sulfur is in group 6. So there's sulfur, and there's just one of them, so 6. We're going to add to that the oxygen. Well, oxygen's also in group 6, so it's going to have 6 valence electrons, but there's 4 of them, so we're going to have to say times 4. We also got to deal with the charge. Now, in this case, it's a -2, which means we have 2 extra negatively charged electrons. So we're going to add 2 to this. So that's going to give us a total of 32 electrons that we need to deal with. Again, we're going to look for the least electronegative element. So we have sulfur and oxygen. So here's oxygen. And remember, the electronegativity decreases as we go down. So sulfur is less electronegative than oxygen. So sulfur is our central atom. Next, we're just going to bound the other oxygens around that central atom with a single bond. In the process, we've used up 2, 4, 6, 8 electrons. That leaves us with 24. Now we need to fulfill the octet for each of the outer oxygen atoms. So we got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Now let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so now we've used up all of the electrons. We fulfilled the octet for every single atom, including the central atom. Now it is an ion, so we got to put square brackets with the charge. But remember, it's formal charge that tells us the best structure, not the octet rule. So let's look at this oxygen. We have 6 minus 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is -1. Well, this is single bond, 3 sets of lone pair, single bond, 3 sets of lone pair, single bond, 3 sets of lone pair. Okay, sulfur again, group 6 is 6 valence electrons, minus 1, 2, 3, 4. 6 minus 4 is plus 2. So we have a total, a sum, right? We have the +2 and the 2 negatives and then -2. So the sum of the charges is -2. That just tells us we use the correct number of electrons to begin with. But I have 5 atoms and I have 5 non-zero formal charges. Now we know that we can't have all of them can't be 0, right? Because the sum has to be equal to -2. Ideally, we'd put that -2 on the electronegative oxygen. But again, as we're going to see, most of the times you have to distribute that to 2 of the electronegative oxygens rather than 1. So let's play the same game again, right? So we have a negative formal charge and a positive formal charge. So let's take the electron from that one with a negative formal charge, and let's make it a multiple bond with the one with a positive formal charge. So that looks like this. Now, these 3 atoms didn't change, so their formal charges are all still -1, but these 2 did. So oxygen group 6 minus 1, 2, 3, 4, 5, 6, that's 0. Sulfur's in group 6 minus 1, 2, 3, 4, 5. 6 minus 5 now is +1. Okay, so we're getting better. Well, let's do it again. Here's a -1 formal charge, a +1 formal charge. So I'm going to take this lone pair, I'm going to make it a multiple bond with that sulfur. Now, these 2 oxygens didn't change, nor did that one, so those formal charges remain unchanged, but now we got to reevaluate this. Well, again, we have an oxygen double bond, 2 sets of lone pair, we know that's 0. We have sulfur group 6 minus 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. Now, there's nothing that we're going to be able to do to get this, but the -2 formal charge on a single oxygen. So this is going to be the best structure we can get, right? It's got the fewest non-zero formal charges. The negative formal charges are on the more electronegative elements. Okay, but again, you might have said, well, geez, I did not have to choose this one and this one. I could have chose, this guy and this guy to make the double bonds. Or I could have chose this guy and this guy to make the double bonds. Or I could have chose this guy and this guy to make the double bonds. And again, you can see that the formal charges, they all have 2 non-zero formal charges. They're -1 on oxygen, right, on 2 of the oxygens. So these structures are the most probable structures. So each one of these is called a resonance structure, including these. This is a resonance structure. This is a resonance structure. And all 4 of these are resonance structures. But we're only going to show the most probable structures, which are going to be these 4 structures here with the best formal charges. We're going to put double arrows between all of them to indicate that this is our resonance description. And now I said that these were resonance structures. They are. And they do contribute to the overall structure, but it is very, very small. In this case, probably less than 1%, and 99% plus is actually coming from these 4 resonance structures right here. Okay, so this is our resonance description of the sulfate anion. So again, if you have choice to where you can make these double bonds or put electrons, then you're going to have resonance. Okay, now let's talk about molecular shapes. So here we have two molecules, boron trifluoride and phosphorus trifluoride. They both have a central atom, and then the three fluorines are bound to it. So you would expect that these two molecules would have the same shape, the same molecular geometry. However, the boron trifluoride is actually a flat molecule. We call it trigonal planar. And the phosphorus trifluoride actually looks like a pyramid. And we're going to call it trigonal pyramidal. Trigonal, since there's three, and then looks like a pyramid, so trigonal pyramidal. So there must be something going on here that we can't see. So our trigonal planar and trigonal pyramidal. So the spatial position of nuclei in a molecule determine its general shape, and we call this molecular geometry of the molecule. Molecular geometries are determined by the bond distance. So this is going to be the distance between the two nuclei. The bond angle. Now this is going to be an angle between three atoms. And lone pairs. So lone pairs occupy space around the atom. And it is these lone pairs that generally distort the shape that we might expect for the atoms themselves. This is due through electrostatic repulsion, and we're going to call this the valence shell electron pair repulsion model. So here, let's look at carbon tetrachloride. So we have a carbon as our central atom, and then it's surrounded by the four chlorine atoms. Its bond distance goes from the center of the atoms, and we can see that it has a bond distance of 1.78 angstroms. And now keep in mind, this is a nice convenient way of looking at it, the ball and stick model, but the reality is it looks more like this, right? The electrons are actually taking up a whole lot of room, and so the carbon tetrachloride looks like a lumpy ball. We have an ideal bond angle of 109.5 degrees, and we're going to find that's true for these what we're going to call tetrahedral molecules. So where does that name come from? Well, basically, all we're going to do is use planes to connect each of the outer atoms, and that looks like this. And this geometric shape is called a tetrahedron, and therefore we're going to call this a tetrahedral molecule. Now, the valence shell electron pair repulsion model, or VSEPR, is going to dictate the shapes of these molecules. Like I said, the electrons of both the bonds and the lone pairs are repulsing each other. So they're going to try to get as far away from each other as they possibly can. And this is what's going to determine the molecular geometry of any molecule. So note that an electron pair refers to a region of electron density around the central atom. So a single bond, a double bond, or a triple bond simply counts as one region of electron density. And also the lone pair electrons are also going to occupy one space. So there will be also a region of electron density. So if we have two regions of electron density, well, that's got to be a linear, right? So they're as far apart as they possibly can be. So the ideal bond angle will be 180 degrees. If we have three regions of electron density, they're going to sit in a flat plane, and they're going to be 120 degrees apart from one another. So again, this is the trigonal planar structure. Okay, and these are what we're going to call our standard electron geometries. So this could be two atoms, you're right? This could be the bonding electrons for those atoms, and then this could be a lone pair, or they could all three be bonds. And as we've seen, if we have four regions of electron density, that's going to be a tetrahedral. And so that's going to have an ideal bond angle of 109.5 degrees. And all of these are 109.5 degrees. These will all sit in the same plane. And then this is coming out of the screen at 109.5. And this is going back behind the screen at 109.5. If we have five regions of electron density, we're going to call that trigonal bipyramidal. This has two sets of angles. So we have the axial positions here and here, so above and below. These are 180 apart from one another. And then we have an equatorial. So this is a plane that sits perpendicular to the axial positions. And this is basically a trigonal planar in the middle here with their bond angles, ideal bond angles being 120, and then of course 90 degrees from the axial to the equatorial position. And if we have 6 regions of electron density, we're going to call that octahedral. So basically, again, we have the axial positions, one above and one below, and then a plane of 4 regions of electron density. These sit in a perfect square, and you can see that the ideal bond angle between all of the atoms are going to be 90 degrees. Now, the steps for predicting molecular geometry. First, you got to draw the Lewis dot structure. Then you're going to count the total number of bonding regions and lone pairs around the central atom. Again, remember, each bond, whether it be a single, double, or triple, counts as one region of electron density. And of course, each of the lone pairs counts as a region of electron density. Then we're going to arrange the bonding regions and lone pairs in one of the standard electron geometries that we just discussed to minimize the electron repulsion. So let's try beryllium hydride. So we got Be and then 2 hydrogens. So first we got to determine how many electrons we're going to need. Well, beryllium has 2 electrons. The hydrogen has 1 electron each. That's a total of 4 electrons. And so we're going to get basically 2 single bonds. Notice that there's no lone pairs around the beryllium. We'll also note that we violated the octet rule as well, right? It doesn't have 8 electrons, and that's because it can't. It ran out. So there's our proper Lewis dot structure. We can see that there's 1, 2 regions of electron density. So this thing is going to have a linear standard electron geometry. So they're going to be 180 degrees apart. It's going to look like this. So this molecule, again, we can see that it has just 2 regions and they're 180 degrees apart. And this is what we call the molecular geometry, and it's linear. So if there's no lone pairs around the central atom, the electron geometry is going to be the same as the molecular geometry. So just to sum it up, if we have 2 regions of electron density and they're both bonding, no lone pairs, the molecule is going to be linear. Now, of course, if you only have 2 atoms, you're only going to have 1 region of electron density. We don't really consider this to be a central molecule. They're not really forming molecular orbitals, but it's just forming a single bond between. That could be a single, double, or triple bond, and it's always going to be linear. If we have 3 regions of electron density, so for example, aluminum trichloride, so we're going to draw the proper Lewis dot structure. That's going to look like this. Again, we see that we have 1, 2, 3 regions of electron density around the central atom, again, violating the octet rule because there simply wasn't enough electrons. But again, the formal charges would all come out to 0 for these atoms. And so that, of course, is going to be trigonal planar, where they're all 120 degrees apart from one another. And so that's going to look like this. And so the electron geometry is trigonal planar. And since there's no lone pairs around the central atom, molecular geometry is also going to be trigonal planar. So what if we have sulfur dioxide? So when we draw the proper Lewis dot structure for sulfur dioxide, it looks like this. We have 1, 2, 3 regions of electron density again. So again, that's going to have a standard electron geometry of trigonal planar. So that's going to look like this, again, with the trigonal planar electron geometry. But we cannot see lone pairs. Okay, we can't see these lone pairs, but they do occupy space. These are negatively charged electrons pushing on the negatively charged electrons of the bonds. So since we can't see the lone pair, the molecule looks like this. And we say that it has a molecular geometry of bent. So just to sum it up, if we have 3 regions of electron density, if all 3 of them are bonding with no lone pairs, the electron geometry is going to be trigonal planar, and its molecular geometry will be trigonal planar. If 2 of those regions are bonds and 1's a lone pair, again, of course, it'll have a trigonal planar electron geometry, but it will have a bent or angular molecular geometry. Now, what if we have 4 regions of electron density? Let's look at the molecule methane. So we're going to draw the proper Lewis dot structure. That's going to look like this. We see we have 1, 2, 3, 4 regions of electron density. Thus, it's going to be tetrahedral with ideal bond angles of 109.5. So the electron geometry is going to be tetrahedral. Again, these are all in the same plane. This is coming out towards us, and this is going back behind the screen. So that molecule looks like this. And again, since it has no lone pairs, the electron geometry is going to be the same as the molecular geometry, tetrahedral. Next, let's look at ammonia. So again, we're going to draw the proper Lewis dot structure for ammonia. That's going to look like this. We're going to have 1, 2, 3, 4 regions of electron density. So again, that's going to have a tetrahedral electron geometry. That'll look like this. But again, remember, we can't see the lone pairs. So what we're going to see is something that looks like this. And you can see, again, it looks like a pyramid with 3 sides. And so this thing is going to be trigonal pyramidal molecular geometry. Let's look at water. So when we draw the proper Lewis dot structure for water, it looks like this. Again, we have 1, 2, 3, 4 regions of electron density. Therefore, again, it's going to have a standard electron geometry of tetrahedral. And of course, with the ideal bond angles of 109.5. Again, we can't see the lone pair, so the molecule actually is going to look like this. And so again, it just looks bent. So the molecular geometry is going to be bent. Just to sum it up, if we have 4 regions of electron density, they're all going to have an electron, 4 regions of electron density, they're all going to have an electron geometry of tetrahedral. If there's no lone pair, its molecular geometry would also be tetrahedral. If it has 3 bonds and 1 lone pair, it will be trigonal pyramidal. And if it has 2 bonds and 2 sets of lone pair, it'll have a molecular geometry of bent. Now, if we have 5 regions of electron density, there's something else that we have to take into account here. So we have these axial positions, right? So they're 180 from one another, but they're 90 degrees from this other plane, which we call the equatorial plane, which is basically just a trigonal planar structure. So the ideal bond angle within the plane is 120, and then from the axial to the planar, from the axial to the equatorial positions, it'd be 90 degrees. Now, to minimize electron repulsion, if you have lone pairs, they have to go in the equatorial positions. And that's because it's going to minimize the repulsion that way. So if I put the lone pair here, I'm now within 90 degrees of 3 other sets of electrons. However, if I'm in one of these equatorial positions, I'm now only 90 degrees from 2 of those bonding regions or lone pair. Okay, so that's actually going to be minimized. Have 2 close to the 90 instead of 3. So the lone pair must go in these equatorial positions. So for example, xenon difluoride looks like this. This would be the proper Lewis dot structure for it. And that molecule, again, since all the lone pair have to go in those equatorial position, is going to have a linear molecular geometry. Okay, so for 5 regions of electron density, they're all going to have a trigonal bipyramidal electron geometry. If there's no lone pairs, of course, again, it's going to have a trigonal bipyramidal molecular geometry. If it has 1 lone pair, again, that lone pair's got to go in one of those equatorial positions, and we're going to have what we call a seesaw molecular geometry. If there's 2 lone pairs, they both have to go in these equatorial positions. So we're going to have a T-shaped molecule. And if we have 3 regions of electron density, they all go in the equatorial positions, and we have a linear molecule. And then if we have 6 regions of electron density, it's going to have, all of them are going to have an octahedral electron geometry. And of course, if there's no lone pairs, it'll have an octahedral molecular geometry as well. If we have 1 lone pair, well, all these positions are equal at first, so you can put that lone pair anywhere you want. And now you can see it looks like a pyramid again, except this time it has 4 sides or a square bottom. And so we call this square pyramidal. And if we have 2 sets of electrons, you can put the first one wherever you want, but the second has to go opposite, so 180 degrees away from the other one. Now you can see that that leaves us with a planar molecule, and it's in the shape of a square, so we call this square planar. Now, how does factors like bond length affect the bond angle? Well, if we look at methane, methane, of course, has four regions, 1, 2, 3, 4. So it's going to be tetrahedral. And that's going to have an ideal bond angle of 109.5. And in fact, it's going to equal, every single one of these are going to equal 109.5 because they're all the same. The bonds are all single bonds and the atoms are all the same. So it's going to have an ideal bond angle of equal. So when you're doing your worksheets, I want you to put equal to, less than, or greater than the ideal bond angle. Make sure you do include the equal if it is equal. I want to make sure that you understand and you just didn't forget. Now, let's say we have replaced one of those hydrogens with a chlorine. Well, chlorine is a much larger atom than the hydrogen, and therefore it's going to sit further away from the carbon. Now, I've greatly exaggerated it here, but you get the idea. It sits further away. So here's the bonding electrons, right, for the carbon hydrogen. They're right here. But the bonding electrons for the carbon chlorine are much further away, right? Much further away than they are here. And in fact, chlorine is slightly more electronegative than the carbon. So it's actually pulling those bonding pairs closer to the chlorine, even making those bonding pair of electrons even further away from the others. Well, remember, this is electron repulsion. So these guys are going to be pushing on each other harder than these are here. So what's going to happen is this bond is going to be allowed to relax. It's going to open up. So this bond angle is going to end up being greater than that ideal bond angle of 109.5. And this one's going to be less than the 109.5, right? So this was the greater than the 109.5. Now, you don't need to know the exact bond angles. I do not want you to Google bond angles. I want you to just tell me if they're greater, less than, or equal to the ideal bond angle. Okay. So next, let's look at other factors that affect the bond angle. So we already seen methane, right? And we know that it has an ideal bond angle, of course, of the 109.5, and so they're equal to 109.5. But what if we replace one of these hydrogens with a lone pair? So like ammonia. Well, these take up space again, and they are pushing, they sit closer to the central atom than the bonding electrons do, okay? And so they're pushing on these bonds. They're repulsing one another. So it's going to cause this bond to shrink. It's going to be less than the ideal bond angle, okay? So in this case, it's 107 degrees. But again, all I want you to do is tell me that it's less than the ideal bond angle of 109.5. And if we have two sets of lone pair, well, they're really pushing on these bonding electrons now. So it's really going to shrink up this bond. And so again, we can see for water, it's only 105 degrees. But again, all I want you to tell me is that it's less than the ideal bond angle of 109.5. Now, multiple bonds will also affect the bond angle as well. So here's an example. Here is the ethene molecule. And here we can see we have a double bond. Well, remember, a double bond is a total of 4 electrons compared to the 2 electrons in the bond. And on top of that, remember, we have a pi orbital overlap here. So the electrons are right in the middle. But then we also have the atomic p orbitals overlapping above and below the plane to create that pi bond of the double bond. So there's, again, a lot more electrons here. So it's pushing harder on these 2 bonds here. And so it's going to make this less than the ideal bond angle of 120. In fact, for ethene, it's 117. But again, I just want you to say that it's less than the ideal bond angle of 120. Now, what if we have multiple bonds and lone pairs? Well, here's formaldehyde. We can see that it has a double bond, so it's definitely squeezing it less than the 120. But in addition to that, remember, the oxygen has 2 sets of lone pairs here. And again, they're regions of negative charge, and they're pushing as well, okay, not as effectively being so far away, but they're still pushing. And we can see that we reduced that angle from the 117 for ethene down to 116. But again, I just want you to tell me that it's going to be less than the ideal bond angle of 120. Now, larger molecules have multiple central atoms. So they're going to follow the exact same rules that we discussed before. So here's glycine. So glycine has the structural formula. It looks like this. Again, it's telling you what's bound to what. We can see there's a carboxylic acid at the end here, right? Another way that we could write carboxylic acid. So we have the nitrogen, and it's bound to the two hydrogens, and it's also bound to the carbon, and it has a lone pair. And this carbon, again, has 4 bonds since it's group 4, right? Nitrogen's in group 5. So it has 5 valence electrons. 3 are going to make a bond, and then we're going to have the lone pair like we discussed in class. And then we got the carboxylic acid group right here. Okay, so this has a total of 1, 2, 3, 4 central atoms. Any atom that's bound to more than one atom is going to be a central atom. So the hydrogen here is only bound to 1, so it's not a central atom. This oxygen is only bound to one other atom, so it's not a central atom. So we have these 4 central atoms. And I can see around this nitrogen, there's 1, 2, 3, 4 regions of electron density. So this has a standard electron geometry of tetrahedral. However, one of them is a lone pair. We can't see the lone pairs, and we know then that this is going to have a molecular geometry of trigonal pyramidal. Then this carbon, 1, 2, 3, 4 regions of electron density. So it too has a standard electron geometry of tetrahedral. There's no lone pairs this time, so its molecular geometry is tetrahedral. This carbon has 1, 2, 3 regions of electron density. That means it has a trigonal planar standard geometry. And again, since there's no lone pairs, it has a molecular geometry of trigonal planar. This oxygen has 1, 2, 3, 4 regions of electron density around it. So it is tetrahedral, but 2 of them are lone pairs. So that means its molecular geometry is bent. So it's easy to assign the electron geometries and molecular geometries for each of the central atoms. Now, that would look like this in a perspective drawing. So you can actually draw this knowing that each one of them, right, this one is going to be the trigonal pyramidal molecular geometry, tetrahedral molecular geometry, trigonal planar molecular geometry, and a bent. So I put all of these guys in the same plane. And then this is going back behind the screen. This is coming out towards us. This is going back behind the screen. This is coming out towards us. So you can draw the perspective drawing for any size molecule. Now, that molecule, if we have the computer aid, looks like this. And again, you can see all the same thing, right? These guys are all in the same plane. This is coming out, this is going back, this is coming out, this is going back. So when you draw this, you should be able to picture this. Okay, let's talk about the polarity of a molecule. Now, we talked about the polarity of individual bonds, and we represented that polarity with a dipole moment. So it's this vector. It has a magnitude. So the bigger the difference in electronegativity of the two atoms, the longer the arrow is going to be, the longer the vector is going to be. And it's pointing in a certain direction. It's pointing from the less electronegative atom to the more electronegative atom. Now, remember, dipole moments are vector quantities. So they're going to, a molecule might have polar bonds and not be polar itself. So for example, let's consider carbon dioxide. So carbon dioxide is a linear molecule. This is its actual structure. There's double bonds between the oxygen and the carbon. So these are both double bonds. And we know that the carbon is less electronegative than the oxygen. Right? So that means the lone pairs are closer, the bonding pairs are closer to the oxygen, making it slightly negative, and then, of course, making the carbon slightly positive. And because there's 2 of them pulling in either direction, it's making it twice as positive as the 2 oxygens. Now, again, we're not going to use these partial charges. We're going to use the vectors, right? So it's going to point towards the more electronegative oxygen, and then this one's going to point towards the more electronegative oxygen. Well, we can see that these are actually equal in size, but they're opposite in direction. You could think of this being plus and this being minus, right? Since they're pointing in opposite directions, and therefore they're simply going to cancel each other out. So even though carbon dioxide contains very polar bonds, the molecule itself is nonpolar because of symmetry. Symmetry kills polarity. So if you have a symmetric molecule, so in other words, if you have a central atom, no lone pairs, and all the atoms around it are the same, and all the bonds around it are the same, you're going to have a nonpolar molecule regardless of what its molecular shape is. Now let's look at water. So again, we know that the hydrogen is much less electronegative than the oxygen. So the dipole moment is going to point from the hydrogen to the oxygen. Same thing is going to be true over here. Now we could use vector addition to look at this, right? I mean, right now you should be able to see that they are equal in magnitude, but they are not pointing directly at one another. They're both pointing in an upward direction. So if we use vector addition, we could say, well, okay, this vector can be represented by one vector going up to this point and then one over to that point. And the same thing over here, one up, one over. We can see that this dipole moment is equal in magnitude, but opposite in direction. So these two are going to cancel. But these two dipole moments are equal in magnitude, but they're pointing in the same direction. So they're simply going to add to give us a net dipole moment going up through the middle of this molecule. Now, the funny thing about water is that if we just took into account the dipole moments of the hydrogen-oxygen bonds, we would expect it to have a certain polarity. But the reality is this thing is much more polar than we would expect. In fact, it has a polarity of 1.94 dBi. So it's an extremely polar molecule for being so small. So the bonds alone don't explain why it has such a high polarity. Well, it's because of those lone pairs that you can't see. Remember what polarity is. It's a shift of charge from one side of a molecule to the other side of the molecule. Well, the electrons are pure negative charge, so it's going to help in that. Now, it helps in a complicated way, but it does contribute to the overall dipole moment. And like I said, a very polar molecule for being so small. Now, we're not going to need to consider the polarity of lone pair, but I do want to explore it a little bit more. Okay, so water, again, very polar molecule because we lost our symmetry with those lone pairs. Now, molecular compounds can be polar or nonpolar, but it's kind of irrelevant for ions. Now, we will say that, discuss and say that ions can be polar or nonpolar, but generally it's just not applicable to what we're talking about. So when we have an ion, a polyatomic ion, we're simply going to say that for the polarity that it is not applicable. Now, two simple rules to help determine molecular polarity, and there are many exceptions. If there are lone pairs on a central atom, the molecule is probably polar. Now, there was one exception, two exceptions actually, that we actually seen, and that was for a trigonal bipyramidal structure that has three sets of lone pair. Remember, all three sets of those lone pairs sat in the equatorial position, and we ended up with a linear molecule. Well, that linear molecule is going to be nonpolar if the two atoms it's bound to are the same, because those dipoles would cancel. So also would be true for the square planar structure that came out of the octahedral electron geometry. Again, if all the atoms are the same around that central atom, they're all going to cancel one another. And again, you'd have a nonpolar molecule, even though you have lone pair. Now, those are going to be the only exceptions that we really deal with. Now, I want to talk about how these lone pairs, again, affect things. So here we have ammonia. So again, the hydrogen bound to the nitrogen. So the dipoles are all pointing towards the nitrogen. And we have this lone pair sitting on top. So ammonia, even though, again, it's a very small molecule, it still has a very high polarity at 1.42 dBi. If we look at nitrogen trifluoride, well, this time, the fluorine is more electronegative than the nitrogen. So this time the dipoles are all pointing away from the nitrogen, but we also have this lone pair up here as well. And so this one has a strikingly low polarity at 0.24. Again, we would simply say that this molecule is polar because we're going to ignore taking into account the lone pairs, and we're just going to be looking at the polarity of the bonds. But it is important to understand how these lone pairs actually affect things. Now, if there are different types of bonds on the central atom, so single bonds mixed with double bonds or triple bonds, the molecule is probably polar again. Remember, there's going to be more electrons on one side of the molecule than there are on the other because of the differing number of electrons within the bonds. And also, if they have different atoms. So here we have a central carbon, and it's bound to three hydrogens. Okay, it's bound to 3 hydrogens. And remember, the carbon-hydrogen bond is essentially non-polar. That's why there's no dipole moments here. And then the fluorine, which is much more electronegative than the carbon. And so we have we're going to have a polar molecule because, again, we lost symmetry this time because of different atoms around the central atom. This is a very polar molecule, 1.85 to bi. So you can see that there's a huge difference in electronegativity between the carbon and the fluorine. Okay, so next, let's talk about hybridization. Now, we're going to talk about this in much greater detail in class, but I just wanted to go over it real quick so that you understand where these hybrid orbitals are coming from, and I'm going to show you a really easy way to assign hybridization. So let's look at carbon. So carbon, you can see this is the orbital diagram for it. And these are going to be our valence electrons. Those are going to be the ones that really take part in the chemistry. And we'll notice that it has 2 electrons paired up in the s orbital and then only 2 unpaired electrons. Well, remember, to form bonds, to form covalent bonds, you have to have an unpaired electron in one atom, and that orbital is going to overlap with an unpaired electron in that other atom's orbital to form a covalent bond. But we know that carbon usually forms 4 bonds, right? 4 single bonds, a double and 2 singles, 2 doubles, a single and a triple, but 4 bonds in total. So this doesn't really make sense. Well, what happens in nature is that these atomic orbitals morph or hybridize into what we call molecular orbitals. So basically what it does is it takes this 2s orbital and all 3 of these 2p orbitals, and they morph them into 4 molecular orbitals. Notice that the name is sp3. So these are 4 sp3 molecular orbitals. So that's how easy it is to assign for hybridization. You have 1s, you're going to have 3 p's, and you have 5 Ds if now they're not available for n equals 2, period 2 elements, but for period 3 elements and higher, there's also those 5 D orbitals available. So you're going to always use the lowest energy one first, which is the S. Then you're going to use the P, which is a little bit higher in energy. And then if you need more than 4 orbitals, then you're going to start using the atomic D orbitals. So now you can see we have 4 unpaired electrons and we can make 4 bonds. So it's a tetrahedral structure since it has 4 regions of electron density. So sp3 hybrid orbitals form a tetrahedral structure with 1, 2, 3, 4 sp3 hybridized orbitals. And if it's methane, well, each hydrogen atom has an unpaired electron, and that unpaired electron in that 1s orbital is going to overlap with the unpaired electron in this sp3 hybrid orbital, forming the carbon-hydrogen covalent bond. And you can see the same thing is happening at all 4 locations, making the 4 carbon-hydrogen bonds. Okay, now steps for determining hybridization. First, you got to write the Lewis electron dot formula for the molecule. You're going to use VSEPR to determine the arrangement of electrons around the central atom, which would be the electron geometry, from the geometric arrangement of the bonding regions and lone pairs, determine the type of hybridization, right? You're just going to count them up. How many regions of electron density are there? And then again, you're going to start with the S, use as many P's of the 3 P's that you need. And then if you do need more, you could use some of the D's. And then you're simply going to assign the valence electrons one at a time to the hybrid orbitals. After all the orbitals contain a single electron, so again, we're following Hund's rule, then we're going to begin pairing them up. And these are going to be the lone pairs around that particular atom. And then bonds are going to be formed between the singly occupied hybrid orbitals. And then the lone pairs will be the ones that are paired up. So let's look at sulfur tetrafluoride. So it has a Lewis dot structure that looks like this. And so you can see that we have 1, 2, 3, 4, 5 regions of electron density. So we need 5 molecular orbitals. So we're going to use the 1s, all 3 p's, and then 1 d. So this is going to be called sp3d hybrid orbitals. And since there's 5 regions, they're going to have trigonal bipyramidal structure. Okay, so it's that easy for assigning hybrid orbitals. You just count the regions, the regions of electron density, just like we did to determine its electron geometry of trigonal bipyramidal, and then simply assign the hybridization using the S first, as many of the P's of the 3 P's that you need, and as many of the D's that you're going to need. So what does that look like in the orbital diagram? Well, here's our sulfur, right? And we need 1, 2, 3, 4, 5 regions. So we're going to use 1, 2, 3, 4, 5, right? That gives us our sp3d. That's our 5 sp3d hybrid orbitals. Notice that we leave the atomic orbitals alone if we don't need them. And it's those atomic orbitals that are going to form the multiple bonds. There'll be one of them will be one of these molecular orbitals. That's going to be the sigma bond. And then we're going to use the unused, usually they're p orbitals, the unused orbitals to make the pi bonds of our double bond or triple bond. And again, we talk about that a lot more in class. So we're going to start filling them singly according to Hund's rule. So 1, and we have a total of 6, right? 6 valence electrons that we need to use up. So we got 1, 2, 3, 4, 5. So now they're all singly filled with the same spin. And now we can come by and pair them up. And so there it is. Now you can understand why this structure looks like it does. There's our lone pair, right? And then each one of these overlaps with an unpaired electron in the fluorine to form those sulfur fluorine bonds, right? Those sigma bonds. So there it is. There's why sulfur tetrafluoride looks the way it does in the Lewis dot structure. So if we have 2 regions of electron density, we're going to have sp hybrid orbitals. And again, only central atoms have these molecular orbitals. The outer atoms would have only their atomic orbitals. So it's only the central atoms that hybridize. If we have 3 regions of electron density, we use the 1s and 2p. So these are our 3 sp2 hybrid orbitals, and they have an electron geometry of trigonal planar. And then if we have 1, 2, 3, 4 regions of electron density, that means we're going to need 4 molecular orbitals. So we're going to use the 1s and all 3p. So these are the 4 sp3 hybrid orbitals. And again, that's going to be tetrahedral electron geometry. And if we have 1, 2, 3, 4, 5, again, we're going to need the s, all 3p, and 1d to give us our 5 molecular sp3d hybrid orbitals. And again, they'll be trigonal bipyramidal. And then finally, if there's 6 regions of electron density, we're going to have to use the 1s, all 3p, and 2 of the d's to form our 6 sp3d2 hybrid orbitals. Now, multiple bonds don't allow rotation, but single bonds can rotate freely. So between these 2 carbons, this can just rotate right around with little problem at all. Now, the higher the temperature, the faster and easier it can rotate. At lower temperatures, it might get stuck in one position or the other until enough energy comes in, allows it to spin. That would be due to just trying to minimize any kind of electron repulsion. But when you have a double bond, they're fixed. They cannot move because remember, those atomic p orbitals are coming out. They're coming out towards us and behind us on both of these guys and overlapping. And that's what prevents them from rotating. So unlike these 2 molecules are exactly the same molecule because you simply rotate it back and you get the same molecule. In this case, they cannot. So these are 2 very different molecules. They have very different properties. So for example, this trans 1,2-dichloroethene, it is nonpolar because the dipole moment's pointing from the carbon towards the chlorine here and from the carbon to the chlorine here. You can see that they're basically equal and opposite, and so they're canceling, and so this molecule is nonpolar. The cis 1,2-dichloroethene, on the other hand, this is a polar molecule. Again, since they can't rotate because of the double bond, the dipole moment is pointing down in this way, and it's pointing down in this way. We can see that they're not canceling. So this has a net dipole moment going straight down through the molecule, and this molecule is polar. So they have very different physical and chemical properties, even though they're composed of the same atoms and same number of atoms. We call these isomers. So this is the cis-trans isomers of dichloroethene. Okay, so this is just basically to sum up everything that we've talked about so far. You can find this in your lab manual. It just gives you how to draw the perspective drawing for each one of these electron geometries. Okay, so again, we're going to draw the perspective drawing from the electron geometry, not the molecular geometry. And then, of course, the hybridizations that go with each one of these. So let's go through and do a couple of examples. Let's write the bond angles, electron molecular geometries, polarity, and hybridization for ammonia. So our first step, of course, is to determine how many valence electrons we're going to need to use. So we need to look at each of the atoms. So for nitrogen, if we could see that nitrogen's in group 5, so it has 5 valence electrons, then we're going to add to that the hydrogen. Well, hydrogen's in group 1, so it has 1 valence electron, but there's 3 of them, so we got to multiply that by 3, and that's going to give us a total of 8 electrons that we need to deal with. Our next step is going to be to draw the skeleton structure. We're going to put the least electronegative atom in the central atom. Well, that would be hydrogen. But of course, we know that hydrogen can never be a central atom because it can only ever form one bond and has no lone pair. So in this case, we got to break that rule already, and nitrogen is going to have to be the central atom. So we're going to put nitrogen as our central atom. And now we're just going to do a single bond between the nitrogen and then the 3 hydrogens. So there's 1, 2, 3. So there's our 3 single bonds. Now at this point, we've used up 2, 4, 6 electrons. So now we still have 2 electrons left over that we need to deal with. Well, we still didn't fulfill the octet for the nitrogen. So we're going to put that lone pair right there. Now we've used up all of the electrons. But remember, it is not the octet rule that determines if we have the most probable structure. It is the formal charges. So hydrogen again is in group 1, right? So 1 minus 1 is 0. This is the same, hydrogen with a single bond, hydrogen with a single bond. Nitrogen, as we've seen, was in group 5. So 5 minus 1, 2, 3, 4, 5. 5 minus 5 is 0. So this is going to be the most probable structure. Since there's 1, 2, 3, 4 regions of electron density around the central atom, this molecule is going to have an electron geometry of tetrahedral. Well, the perspective drawing looks like this. We have our central atom. In the same plane, we have one one region of electron density here at 109.5, another one here in the same plane. Then coming out of the screen at 109.5 degrees, and then one going back behind the screen at 109.5 degrees. So there's our perspective drawing. Now the hybridization, well, since we got to do the electron geometry and count the regions of electron density, well, that's the same information that we need for hybridization. So if we have 1, 2, 3, 4 regions of electron density, we need 4 molecular orbitals. So we'll use the 1s and then all 3p. So this thing is going to be sp3 hybridized. Next, let's fill in the atoms, right? Nitrogen was our central atom, and then we had the 3 hydrogen. Well, that means that our lone pair is simply going to go up there. So this molecule then looks like this. But again, you can't see the lone pair. So its molecular geometry then is going to be trigonal pyramidal. Next, let's talk about the bond angle. Well, for a tetrahedral, the ideal bond angle is 109.5. But because this lone pair is pushing down, it's going to be less than 109.5. Now, don't forget to put that on your perspective drawing. Again, make sure it says less than, greater than, or equal to that ideal bond angle on your forms. Okay. Next, let's talk about the polarity of the molecule. Well, again, we got to look at the individual bond polarities themselves. So we can see that nitrogen, right, is much closer to fluorine and therefore much more electronegative than the hydrogen is. So our dipole moment is going to point from the hydrogen up towards the nitrogen. Well, the same thing is going to be true there. The same thing is going to be true there. Again, these are not pointing directly to each other, not in the same plane. So they're not canceling. We're going to have a net dipole moment going right up through the middle of this molecule. And so this molecule is going to be polar. Let's try another example, boron trifluoride. Again, we're going to go through the same steps. We got to determine the number of valence electrons. So we'll look at boron first. Boron, as you can see, is in group 3, so it has 3 valence electrons. And then we're going to add to that the valence electrons for the fluorine. Fluorine is in group 7, so it's going to have 7 valence electrons, but there's 3 of them, so we have to say times 3. That's going to give us a total of 24 electrons that we need to use to make the correct Lewis dot structure. So again, we want the least electronegative. Well, here's boron, and fluorine, of course, is the most electronegative. So boron's definitely the least electronegative of the 2. So that's going to be our central atom. And now we're just going to use single bonds to connect these other 3 fluorine to that boron, right? So there's our 3 other bonds. And again, it doesn't matter where you put them or how you write them, okay? Because this is just a Lewis dot structure. This is just telling us what atoms are bound to what, whether they're single, double, or triple bonds, and where the lone pairs are. Okay, now we've used up 2, 4, 6 electrons. We still have 18 electrons to deal with. So we got to fulfill the octet of the outer, more electronegative atoms first. So this fluorine has 2. So 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay, now let's take a quick count here. 2, 4, 6, 8, 10, 12, 14, 16, 18. Well, now we've used up all of our electrons. We don't have any left. We did not fulfill the octet for boron. But remember, this is just getting us to the most probable structure the quickest. Now we need to look at the formal charges. So again, fluorine's in group 7. So 7 minus 1, 2, 3, 4, 5, 6, 7 is 0. This is identical, right? It's a fluorine single bond, 3 sets of lone pair. Same thing here. So these are all zeros. Boron, as we've seen, is in group 3. So 3 minus 1, 2, 3. 3 minus 3 is 0. So this is the most probable structure. So next, we need our electron geometry. So there's 1, 2, 3 regions of electron density. So it's going to be trigonal planar. Our perspective drawing end is going to look like this, right? These are all in the same plane, and these are about 120 degrees apart from one another. Our central atom was the boron, and then we had the 3 fluorine around it. The hybridization, right? Since we have 1, 2, 3 regions of electron density, that means this thing is going to be, we need 1 s and 2 p's, so it's going to be sp2 hybridized. Now, since there's no lone pair, the molecular geometry is going to be the same as the electron geometry. So it's going to be trigonal planar. Now, for trigonal planar, the ideal bond angle is 120 degrees. Now, since these are all the same, and there's no lone pairs pushing or no double bonds pushing or different atoms around it, it's going to have the ideal bond angle of equal to 120 degrees. Again, don't forget to put that on your perspective drawing. Next, let's look at the polarity of the molecule. Well, again, we can see that boron, again, is much less electronegative than the fluorine, so the dipole moment is going to point from the boron straight to the fluorine. Same is true here, and same is true here. But this molecule is perfectly symmetric. It has no lone pairs. All the outer atoms are the same, and all the bonds are the same. They're all single bonds. So they're going to cancel one another, and this molecule is going to be nonpolar. Again, remember, symmetry kills polarity. Okay, let's try another one. So this time we have carbon monobromide trihydride. And so again, we got to count up the valence electrons. So let's start with the carbon. Again, we can see that carbon is in group 4, so it has 4 valence electrons. Next, we're going to add the electrons for the bromine. The bromine is in group 7, so it has 7 valence electrons. Now we're going to add that to the hydrogen. Well, hydrogen we know is in group 1, so it has 1 valence electron, but there's 3 of them. So we got to times 3. Add them up, we get a total of 14 electrons that we got to deal with. Next, we got to choose our central atom. Well, again, hydrogen is the least electronegative, but it can't be the central atom. So let's just look at carbon and bromine. Well, I can see bromine is closer to fluorine than carbon, so carbon is going to be less electronegative, and that's going to be our central atom. Now we're just going to bond these other 4 atoms around the carbon using single bonds. So there's the bromine and then the 3 hydrogen. We've used up 2, 4, 6, 8 electrons in the process. We got 6 left over to deal with. We're going to fulfill the octet for the outer, more electronegative atoms first. So the bromine has 2, 4, 6, 8. Now we've used up 6 electrons. We have none left. But again, we got to check those formal charges. Well, again, hydrogen was in group 1. 1 minus 1 is 0. Same thing for this hydrogen, same thing for this. Bromine's in group 7, minus 1, 2, 3, 4, 5, 6, 7, so it's 0. Carbon's in group 4, minus 1, 2, 3, 4, so it is also 0. So this is the most probable structure. There's 1, 2, 3, 4 regions of electron density around the central atom, so it's going to be tetrahedral electron geometry. That's going to have a perspective drawing that looks like this. Again, these are 109 apart in the same plane, and then one coming out at 109.5 and one going back behind the screen at 109.5. Carbon's our central atom, and then you can put the wherever you want. I'm going to make these 3 the hydrogen and then put the bromine up here. So the hybridization, 1, 2, 3, 4 regions of electron density. So we're going to need 1 S in all 3 P. So this is going to be sp3 hybridized, or 4 sp3 hybridized molecular orbitals. So that molecule is going to look like this. Now, as far as the bond angles, the molecular geometry then, since there's no lone pairs, is going to be tetrahedral as well. Now, let's look at the bond angles here. Now, remember, these bonding electrons are much further away, so it's allowing these guys to relax or push harder on each other, so they're forced up. So this bond angle here is going to be greater than 109.5, and this one's going to be less than 109.5. Again, don't forget to put that on your perspective drawing. Now, as far as polarity is concerned, well, we know that the carbon-hydrogen bond is essentially nonpolar. You just have to remember that. But we do need to look at the carbon and the bromine. Well, again, bromine's closer to the fluorine, so it's more electronegative than the carbon. And so the dipole moment is going to point from the less electronegative carbon to the more electronegative bromine. There's no other dipole, so this thing is not being canceled out. So this molecule is polar. Okay, let's try another one. Let's try the sulfur tetrafluoride. So again, we got to count out the number of valence electrons. So sulfur, okay, we can see that sulfur is in group 6. So there's going to be 6 valence electrons. Then we're going to add that to the fluorine. Fluorine is in group 7, so there's 7 valence electrons, but there's 4 of them, so we have to say times 4. So that gives us a total of 34 electrons to deal with. The sulfur is obviously less electronegative than the most electronegative element, fluorine, so sulfur is going to be our central atom. We're going to single bond the other 4 fluorines around the sulfur. We've used up 2, 4, 6, 8 electrons, so we're going to subtract the 8 electrons. Now we have 26 electrons left to deal with. We're going to fulfill the octet for the outer more electronegative atoms first. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we used up 24. We still have 2 electrons left. Now remember, when we have extra electrons, and we've already fulfilled the octet for all the atoms, including sulfur, we're going to put those extra electrons around the larger atom, right? Remember, the atoms get bigger as we go down, and they get smaller as we go from right to left. So sulfur is bigger than the fluorine, and so we're going to put that lone pair on the sulfur, okay? Okay, so there it is. But again, we violated the octet rule, but that octet rule is just trying to get us to the most probable structure quickly. So now what we need to do is actually look at the formal charges. So again, fluorine's in group 7. 7 minus 1, 2, 3, 4, 5, 6, 7 is going to be 0. Same thing with this fluorine, same with this and this. Sulfur's in group 6, minus 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. So this is the most probable structure then for sulfur tetrafluoride. Okay, so there's 1, 2, 3, 4, 5 regions of electron density. So our electron geometry then is going to be the trigonal bipyramidal. That perspective drawing is going to look like this. Again, we have our central atom, one straight up, one down, and then all in the same plane, we have these three in this trigonal planar structure, all 120 apart, 90 degrees, of course, from the axial to the equatorial positions. Now, remember, we have a lone pair, and lone pairs have to go in one of these equatorial positions. Okay, so there's our sulfur, and I'm going to put the lone pair over here. It's got to be in one of these three positions. So now I can put the other fluorines in. There's my other fluorines. And now hybridization, well, again, there was 1, 2, 3, 4, 5 regions of electron density. So we're going to have to use the 1s, all 3p, and 1d to form our 5 sp3d hybrid orbitals. So that molecule looks like this. Now, the molecular geometry, remember, we can't see the lone pair. And if we rotate this thing, it looks like this. Well, that's a seesaw, right? Here's our plank, and here's the fulcrum that holds it, right? So this has the molecular geometry of seesaw. Okay, now let's talk about the polarity of the molecule. So again, we know that let's talk about bond angles. Okay, so we know that this ideal bond angle is 90 degrees, but remember, this lone pair is pushing down on it, right? It's pushing it closer to this plane. Same thing is true here. So this is also less than 90. And then this ideal bond angle would have been 120 degrees. But again, it's pushing on that bond as well. So it's squeezing this bond less than 120. So make sure you put that on your perspective drawing. Now let's look at the bond angle on the lone pair. Well, that's not possible. Bond angles are between 3 atoms. So there is no bond angle to the lone pair. Remember, we can't see the lone pair. Okay. Okay, next let's talk about the polarity. Well, again, we could see that phosphorus, again, is less electronegative than the fluorine. So that dipole moment is going to point straight from the phosphorus up to the fluorine. Same thing true here, here, and here. Well, this time we lost symmetry because of this lone pair, right? So these two are canceling one another, but these two are pointing out in this direction. So this molecule is going to be polar. Okay, let's try one more. Iodine tetrabromide anion. So again, we got to count up the electrons. So let's look at the iodine. Iodine is in group 7, so that's going to be 7 valence electrons. We're going to add that to the bromine. Bromine's also in group 7, so that's another 7 valence electrons, but there's 4 of them, so we're going to have to say times 4. Then we got to take into account that charge. Well, it has a -1 charge. That means it has 1 extra negatively charged electron, so we're going to add 1. So that gives us a total of 36 electrons that we need to deal with. Next, we want to put the least electronegative atom, which is the iodine, right? It's less electronegative than the bromine. Bromine sits closer to the fluorine, so it's more electronegative. So iodine is going to be our central atom. Then we'll single bond all those 4 bromine around the iodine. Again, doesn't matter where you actually draw it. This is just showing us what is connected to what. We've used up 2, 4, 6, 8 electrons. We still have 28 electrons to deal with. We're going to fulfill the octet of the outer more electronegative atoms first. So this bromine has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So we used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. We still have 4 extra electrons to deal with. So again, we're going to put them as lone pairs around the central atom. So we'll put 1 here and 1 here. Now, again, we really violated the octet rule for iodine, but let's see what the formal charges have to say. So bromine in group 7 minus 1, 2, 3, 4, 5, 6, 7 is going to be 0. Oops, got to put the square brackets in the charge since it is an ion. Okay, so the formal charge of this bromine 0. This bromine is the same, and the same. Now the iodine's in group 7, minus 1, 2, 3, 4, 5, 6, 7, 8. It has a formal charge of -1. Well, the sum of the formal charges is equal to the charge. So that's correct. That means we simply use the right number of electrons. Now, the one thing that we might not like is that we just put the negative formal charge on the less electronegative atom. So this is, again, one of these exceptions that I'm talking about. Halogens generally do not like, so the group 7, right, generally do not like to form double bonds. Sometimes they do, but they usually do not. So in this case, yes, we're going to put the negative formal charge on the central iodide because, again, the halogens don't like to form multiple bonds. Okay, so now we have 1, 2, 3, 4, 5, 6 regions of electron density. So that's going to be octahedral electron geometry. That is going to look like this. Again, we have our central atom, one straight up, one down, and then 1, 2, 3, 4 in this same plane, which is in the form of a square. So the square planar central part, but the whole thing is octahedral. We'll put our iodide in the center. Now we have these lone pairs that we need to deal with. So you can put your first lone pair anywhere, because all these positions are equal. So I'll just put it here. But now once I place that first set of electrons, the next set of electrons must go opposite it. And then I can fill in the rest with the bromine. So there it is. Now the hybridization. Again, we have 1, 2, 3, 4, 5, 6 regions. So we need 6 molecular orbitals. We're going to use the 1s, all 3p, and 2d to form those 6 sp3d2 hybrid orbitals. So that molecule now looks like this. Its molecular geometry, well, these all sit in the same plane, and it looks like a square when you turn it on its side. So it is square planar. Now the bond angles, well, the ideal bond angles are 90 degrees. Now you might think that that might change because we're pushing on with a set of lone pair here, right? They're pushing down on it. But there's also a lone pair underneath pushing just as hard back up. So this time the bond angle is the ideal bond angle. It is equal to 90 degrees. So don't forget to put that on your perspective drawing. Now, polarity. Well, we got to look at the iodide bromine bond. So again, we're going to basically say that it's not applicable since it's an ion. It really doesn't matter. But it is still got some polarity to it. So again, the iodine is less electronegative than the bromine. So they're all going to point out towards the bromine. Okay, so again, they're going to point from the less electronegative iodine to the bromine. But if we look at that structure again, we can see that this one is canceling this one, and this one is canceling this one. So this would be a non-polar molecule or polyatomic ion.